So far, every time we've done a new probability problem, we've calculated a new probability function, and it's based on the sample space. And you've probably seen, even if the sample space is quite small, it's quite tedious calculating that probability function. However, it turns out that there are several cases where the probability function crops up again and again and again, and if you know what probability function your problem uses, you can save a lot of hard work. We're going to look at two main discrete probability functions, the discrete uniform probability function and the binomial function. The discrete uniform probability function models any situation where the outcomes all have equally likely probability. So these are things that we've seen, for example, a fair dice roll or things like that. So now we're going to put together the theoretical formulae so that you don't need to go through all the calculations yourself. So we start out by assuming that we have a random variable with space 1, 2, 3 all the way up to n for some n. And that the likelihood of each of these values is equally likely. So the probability of getting 1 is the same as the probability of getting a 2, and so on. So since our probabilities are all equally likely, we must have that our probability function is a constant. So it gives us the same value for any value of x in our variable space. And then we can work out, since we know that the sum of our probabilities has to equal 1, it must be that our probability function is always going to be 1 over n. So for example, if we take n to be 5, then our probability density function is 1/5 for every value of x over our space 1, 2, 3, 4, 5. And if you plot it, then it's no surprise, you just see constant dots for each of the possible values. And here are the calculations. If you would like to check that this makes sense, if you head on over to the textbook, you can use Sage to plot the probability of a discrete uniform distribution by changing for different values of n. So for example, you might put n equals 7, and then you'll see that each of the values is 1 over 7, and so on. So we could go all the way up to 1 over 9. Now we've got that the probability of each particular outcome is 1 over 9, and you can work anything out from there. So let's just take a picture of that and pull it back into the notes. So no surprises here. But what we'd like to have is the theoretical properties of our discrete uniform probability function. So we already know that the probability is going to be 1 over n, where n is the number of outcomes that we have, assuming they're all equally likely. And it turns out that the average value, or the expected value, the mean, is going to be 1 plus n over 2, and the variance is given by n squared minus 1 over 12. So this is something that you do need to know, and it makes life quite a lot easier. So for example, if we want to say what is the probability function for a fair 6-sided die, well, we have, so being 6-sided means that we have 6 outcomes. So our random variable space is 1, 2, 3, 4, 5, 6. So our f of x is going to be 1 over 6. Our mu, which is our mean, is going to be 1 plus 6 over 2, which gives us 3.5. So we might be wondering, what does this 3.5 tell us? Well, remember, mu is the expected value, or the mean, or possibly even the average, if that's how you want to think about it. So this says if you roll a fair six-sided dice many, many times, and you take the average of the outcomes that you get, the average that you'll get would be 3.5. Now that might have been fairly straightforward to calculate by hand, but you can imagine that if you wanted to find out the probability function and mean for a 20-sided dice, that would be a bit of a pain. But with this formula, we know that here we've got 20 outcomes, and we can plug this straight in. So our probability function is going to look like just 1 over 20. Our mu is going to be 1 plus 20 over 2, which gives us 10.5. So if you have a 20-sided dice and you keep rolling it and you make a note of what you get each time and then you add up an average, that's going to give you 10.5. So that's a discrete uniform probability function called uniform because the probability of any particular outcome is the same. So we have equally likely outcomes, so you get a uniform or flat distribution. Next up, we have what's called the binomial distribution. We won't use this very much, but it is used to introduce a distribution we will use a lot. So often, practical problems involve simply measuring whether something worked or didn't work. And here we're using success and failure simply to indicate something happened or didn't happen. It's not having a moral or subjective meaning. As we've said before in a previous section, it just means that something happened or didn't happen. So, in the situation where we've got a single trial that's performed and the result is determined either as a success or failure, this is called a Bernoulli event. And if you wanted to create a model for this, you could have a probability function using a random variable over the space 0, 1, where 0 means things didn't happen and 1 means it did happen. And then if we are going to call little p the probability of a success, or getting a 1, then our probability function would look like this. So let's just take a moment to make sure we understand what's happening over here. So remember that our x is coming from our random variable over the space R. So x is really either something happened or it didn't happen. And this p over here is the probability of success. And here we're thinking of success, i.e. x is equal to 1. Okay, so if, for example, we can think about an example of flipping a coin, where we're going to count, so we're going to flip a coin. Getting heads is a success. Getting tails is failure. If it's a fair coin, then our probability of success is the probability of heads, which, if it's, as I say, a fair coin, that's 0.5. And then our probability function will be f of 0 is equal to 0.5 to the 0 times 1 minus 0.5 to the 1 minus 0. And if you have a look at this, so 0.5 to the 0 is 1, 1 minus 0.5 is 0.5 to the 1, which is 0.5. So, unsurprisingly, the probability of a failure or getting tails is 0.5, and because it's a fair coin, the probability of getting heads is 0.5. You might say, okay, suppose it's not a fair coin. So, not a fair coin, what do we get? Well, let's say that suppose that our probability of getting heads in this case is 0.6. Well, then our probability of getting 0, which is failure or getting tails, is going to be 0.6 to the 0, 1 minus 0.6 to the 1 minus 0. So that's 1 times 0.4, which is 0.4. So you can see how this works. And our probability of getting heads is 0.6. And notice that these do add up to 1, which is what we'd want. But this is not particularly helpful. Where we actually want a head is a little bit further on. But first, just take a little note here. Notice that p equals 0 means that you always fail, and p equals 1 means that you always get a success. But if you know what's going to happen, then x is no longer a random variable, because you can predict with certainty. So for these kinds of problems, we're always going to assume that our probability lies strictly between 0 and 1. Okay. So as we've said, the Bernoulli distribution is not particularly useful, but it does give us a starting point for one particular distribution, the binomial distribution, in which the number of trials is fixed and x measures the variable number of successes. So, for example, we might have the idea of flipping a coin 10 times, and that's going to be one trial, and we want to think of, when we flip the coin 10 times, how many heads are we going to get? And getting heads might count as a success. So how do we set this up? Well, we're going to consider a sequence of n independent Bernoulli trials. Okay, independent means that what happens in one trial is not affected by what happened before. So not affected by each other. And Bernoulli trials, we've just seen, are success or failure. And we're also going to assume that the likelihood of success, so our probability p on each individual trial, is constant from trial to trial, and as we've just said, lies strictly between 0 and 1. So we're going to let our random variable x measure the number of successes obtained when doing n trials. Okay, so we're going to do some particular number of trials. For example, we're going to flip a coin 10 times, and we're going to let our random variable count, for example, the number of heads that we get. And we want to think about, what does the resulting probability distribution look like? Well, it's called a binomial distribution for good reason, because one of the first things that you'll notice is a binomial coefficient sitting here. So let's just make sure that we're happy with everything in this formula. So remember that our x is an element of our random variable sample space. So in this case, it's going to be 0, 1, all the way up to n. So thinking about our 10 coin flip examples, you might get 0 heads all the way up to, in this case, it would be 10 heads. So that's what our x's are, and we've got them popping up all over the place. Our probability is again the probability of success. And over here, n is the number of trials. Okay, what do these things look like? Well, if we're going to, for example, do 10 trials, so here we're thinking of flipping a coin 10 times, and it's a fair coin, so the probability of heads or tails is the same, it's a half either way. Then what we have is this function over here, and it's over the space 0 to 10. And what does it look like? Well, you'll see that the probability of getting 0 heads is very small, whereas the probability of getting 5 heads is probably the biggest probability that we've got, and the probability of getting all 10 heads is very small. And this kind of fills in with what we would expect. If you flip a coin 10 times, you would be a little surprised if it came up with heads each time and you knew it was a fair coin. And likewise, you'd be a little surprised if you didn't get any heads. But if you got 5 heads, it would seem kind of normal. So this gives you an idea of what this probability distribution looks like. Let's head over to our textbook. So if we head to the binomial distribution, so let's have n of 37, and you can see that's a nice symmetric shape. But what happens if we change the probability? So let's change the probability of success to 4 out of 5. We'll notice that this skews our distribution quite heavily, so that it looks like our highest likelihood, our highest probability is getting 30 successes, whereas getting 0 successes is very unlikely in this case. On the other hand, if we reduce our probability of success down to 3 out of 20, you'll notice now our highest probability is for getting 5 or so successes, and getting 35 or more successes is very unlikely. So changing our probability skews the distribution one way or the other. So here we have an example of 10 and a probability of 1 over 4 for a success. And as you can see, we're skewed towards the lower end of our sample space. So as we had with the uniform distribution, we need to know the distribution statistics. And here it turns out that our mean is n times p. So this is number of trials, and p is our success probability, and sigma squared, which is our variance, also nice and easy, n times p times 1 minus p. And you don't need to think about that, although that gives a measure of the skewness. Alright, so let's use this in practice. So suppose you flip a coin exactly 20 times. We want to determine the probability of getting exactly 10 heads. So that's going to be the first thing that we do. And then we're going to determine the probability of getting 10 or fewer heads. Okay, so we want to solve problem 1. So I've just plotted here, I've just copied here the formula that we need. So remember, x is the random variable we're interested in. In this case, we've got, our x is the probability of getting x successes. That's this whole thing. So if we want the probability of getting 10 successes, then we need, now n is the number of trials. So in this case, that's going to be 20. And we want the probability of getting 10 successes. We're going to assume that our coin is fair, which tells us that our probability of the success is the usual 0.5. So then we have 0.5 to the x, which is 0.5 to the 10, times 1 minus 0.5, 20 minus 10. And if you work this out, that gives us a 20, choose 10. Now, this is actually 0.5. So we've got 0.5 to the 10 times 0.5 to the 10, which is really just 0.5 to the 20. And if you work it out, that's 0.176. So if you flip a coin exactly 20 times, the probability that you will get exactly 10 heads is 0.176. Let's see if this seems likely. So here we've plotted the distribution. So we've got our n is 20, and we have probability of success of 0.5. And if you have a look, here's our x, probability of getting 10. Yep, that looks about right. So now we need to answer the next question, which is, what is the probability of getting 10 or fewer heads? Well, we want the probability that our random variable, i.e. the number of heads that we get, is less than or equal to 10. So obviously, it's going to be bigger than the probability of getting exactly 10. And it's in fact going to be the probability, so let's just write this. So we want the probability that our random variable is less than or equal to 10 is the probability that our random variable is equal to 10 plus the probability that it's equal to 9 plus the probability that it's equal to 8 all the way down to the probability that it's 0. Because each of these values of the random variable satisfy the criterion that they are less than or equal to 10. And you could go ahead and plug this into the formula, and if you do that, you will find that the probability that your random variable is less than or equal to 10 is 0.588, and then some bits. Does this make sense? Well, remember what you're saying here is if you flip your coin 20 times, what's the probability that the number of heads you get will be less than or equal to 10? And you would expect that it would be slightly more than half the time. So let's have a look at an example that uses our binomial distribution. So we're looking at integrated circuit chips, and it happens to be known that 20% of the chips that get created are defective. So immediately we know that our probability of having something wrong, or our probability of being defective, is 0.2. To maintain and monitor the quality of the chips, a sample of 20 chips is selected at regular intervals for inspection. So we know that we're always going to pick 20 things, so our n is going to be equal to 20. And we're going to let x denote the number of defectives found in the sample. So our random variable has a range that goes from 0, because maybe there are no defective chips, all the way up to 20. Maybe all the chips are defective. So if we think about that, we know that 20% of them are defective, so we're going to count a success as finding a defective chip. So our probability of success is 0.2. So the first thing we'd like to ask is, what is the probability that all 20 chips are defective? So here we're saying we want to know that here we're letting x would be 20, and we want the probability that 20 chips are defective. And since this is a case where we're measuring success or failure for 20 things, we're going to use our binomial distribution. So we know that this is going to be 20 choose 20, and then our probability of success is 0.2. We raise that to the power of 20, and then we've got to multiply by 1 minus 0.2 to the 20 minus 20, and if you work that all out, you should get 1.05 times 10 to the minus 14. Does this make sense? Well, it seems quite likely. Not that many of the integrated chips are defective, and it would be very unlikely that we'd get that all 20 of them were defective, and this is a very small probability. A slightly more sensible question to ask would be, what's the probability that 3 or fewer of the chips are defective? So here we're wanting to have that the number of defective chips is less than or equal to 3. So we want to have the probability that x is less than or equal to 3, and this means it's going to be the probability that exactly 3 are defective, plus the probability that exactly 2 are defective, plus the probability that exactly 1 is defective, plus the probability that none of them are defective. And if we go through and work this all out, we've got a 20 choose 3 times 0.2 to the 3 times, so 1 minus 0.2 is 0.8, and that's 20 minus 3, which is 17, plus 20 choose 2, 0.2 to the 2, 0.8 to the 18. So that was our probability that exactly 2 are defective. Our probability that exactly 1 is defective is 20 choose 1, 0.2 to the 1 times 0.8 to the 19. And finally, our probability that none are defective is 20 choose 0, 0.2 to the 0 times 0.8 to the 20. This is a little bit of a pain, but if you plug it into your calculator, you should get a probability of 0.411. So this says that there's about a 40% chance that 3 or fewer of the chips are defective. So this is just an example of how to use the binomial distribution.